A remote stretch of ocean along Russia's far eastern edge became the focal point of a planetary scale adjustment that few could feel, yet instruments across the globe could not ignore. How can a single rupture beneath the sea subtly alter the pace of time itself? What does it mean when the balance of an entire planet shifts by mere centimeters, yet with consequences measurable from space? And how does an event lasting only seconds leave behind signals that ripple through satellites, navigation systems, and the precise ticking of atomic clocks? At 24 minutes past 11 in the morning, local time, a powerful seismic rupture struck beneath the waters east of the Kamchatka Peninsula. The magnitude registered at 8.8, placing it among the most energetic earthquakes ever recorded in modern geophysical history. The epicentral region lay approximately 119 kilometers, or about 74 miles, east-southeast of Petropavlovsk-Kamchatsky, positioned directly along the Kuril-Kamchatka subduction boundary. This boundary marks a relentless collision zone, where the Pacific Plate descends beneath the North American Plate, compressing, locking, and eventually releasing vast amounts of accumulated stress. The rupture itself extended across an immense segment of the plate interface. Seismic inversions and early modeling indicated a fracture zone stretching close to 480 kilometers, or roughly 300 miles, in length and about 160 kilometers, or 100 miles, in width. Along this interface, displacement reached extreme values, with sections of the fault slipping by as much as 9 meters, or nearly 30 feet. That movement occurred in a matter of seconds, redistributing enormous volumes of crustal material and releasing energy equivalent to several 100 million tons of explosive force. Unlike deeper seismic events that dissipate energy before reaching the surface, this rupture occurred at a relatively shallow depth of about 20 kilometers, or 12.4 miles, beneath the sea floor. That shallow positioning allowed the energy to couple directly with the overlying ocean column. The seafloor was abruptly lifted and shifted, displacing vast quantities of water and initiating a chain of wave propagation across the Pacific basin. Within minutes, tsunami monitoring systems began registering anomalies. Alerts were issued across an enormous geographic span, from the northern Pacific coastlines of Alaska down toward the shores of South America. Coastal regions in Japan activated warning systems, urging residents in vulnerable zones to move inland or seek elevated ground. In Hawaii and along parts of the western United States, emergency protocols were triggered, with monitoring stations tracking wave amplitudes and arrival times with heightened scrutiny. Across most of the Pacific, the resulting waves remained within a moderate range. Sea level oscillations typically reached about 1 meter, or roughly 3 feet, enough to generate strong currents and localized flooding, but not widespread devastation. However, conditions near the source region told a far more intense story. On Shumshu Island, near the northern reaches of the Kuril chain, water surged ashore in a towering wave reaching approximately 19 meters, or about 62 feet. The force of that surge overwhelmed coastal infrastructure, sweeping vessels inland and damaging port facilities. In Severokurilsk, the advancing water penetrated inland distances approaching 200 meters, or roughly 660 feet. Industrial sites, including fish processing operations, sustained damage as the surge disrupted both physical structures and supply chains. The localized intensity underscored the uneven distribution of tsunami energy, where proximity to the rupture zone amplifies impact far beyond what distant coastlines experience. Despite the scale of the seismic event, human casualties remained remarkably limited in the immediate region. Authorities initiated evacuations involving more than 2,700 residents from low-lying coastal zones. Structural damage, while visible, did not approach the catastrophic levels often associated with earthquakes of this magnitude. Buildings swayed under prolonged shaking, a kindergarten structure experienced partial facade collapse, and a medical facility showed signs of stress fractures. At an airport in Elizovo, a portion of the ceiling gave way. Yet the overall resilience of infrastructure, shaped by stringent construction practices and regular preparedness measures, contributed to the absence of fatalities. Far from the epicenter, the consequences took on a different form. In Japan, located over 4,000 kilometers, or approximately 2,500 miles from the source, the seismic waves themselves were barely perceptible. However, the response to tsunami warnings coincided with extreme summer temperatures exceeding 40 degrees Celsius or 104 degrees Fahrenheit. Evacuations conducted under such conditions led to numerous cases of heat-related illness. More than 20 individuals required hospitalization due to dehydration and heat stroke, and a single fatality occurred during an evacuation-related incident. These outcomes illustrated how the indirect effects of a seismic event can propagate through human systems in unexpected ways. As the immediate impacts were assessed, a more subtle and scientifically significant set of observations began to emerge. Networks of satellites, ground-based positioning stations, and highly precise timing systems detected anomalies that extended beyond surface damage. The earthquake had not only reshaped sections of Earth's crust, it had altered the distribution of mass within the planet. When large volumes of mass shift closer to Earth's rotational axis, the planet's moment of inertia decreases. This principle mirrors the motion of a spinning figure skater drawing their arms inward, resulting in a slight increase in rotational speed. In this case, the redistribution caused by the earthquake led to a marginal acceleration of Earth's spin. The effect was extremely small, shortening the length of a day by a few microseconds, yet it was measurable through atomic timekeeping systems that track time with extraordinary precision. Comparable seismic events in recent decades have demonstrated similar effects. A major earthquake in Chile during 2010 reduced the length of a day by just over 1 microsecond, while a powerful event in Japan in 2011 produced a reduction of approximately 1.4 microseconds. The Kamchatka event now joins this category of rare tectonic disturbances capable of influencing planetary rotation in a measurable way. In addition to altering rotational speed, the redistribution of mass affected the figure axis, the axis around which Earth's mass is balanced. This axis differs from the geographic axis that defines the planet's poles and governs seasonal tilt. Changes to the figure axis do not alter the cycle of seasons, yet they can be tracked with remarkable accuracy using satellite geodesy. Previous earthquakes have shifted this axis by several centimeters, and early assessments suggest that the Kamchatka rupture produced a comparable displacement. Ground deformation measurements provided further confirmation of the scale of crustal movement. Portions of southern Kamchatka experienced horizontal shifts approaching 2 meters, or about 6.6 feet, toward the southeast. Such displacement, while modest when viewed locally, represents a substantial reorganization of mass when integrated across a region spanning hundreds of kilometers. These movements contribute directly to the observed changes in Earth's rotational characteristics. Claims that the planet's tilt had been altered circulated widely in the aftermath, yet such interpretations do not align with established physical constraints. The axial tilt, approximately 23.4 degrees, remains stable because altering it would require an external torque far exceeding what internal tectonic forces can generate. The earthquake influenced internal mass distribution and rotational dynamics, but it did not modify the orientation of Earth's axis in space. The significance of these changes lies not in their immediate impact on daily life, but in their detectability and the insight they provide into planetary mechanics. Earth's rotation and internal balance are constantly influenced by a range of factors, including atmospheric circulation, ocean currents, and seasonal redistribution of water and ice. These processes typically produce gradual variations. In contrast, a large earthquake introduces an abrupt shift, creating a distinct signal that can be isolated and analyzed with precision. As global monitoring systems continued to process incoming data, the Kamchatka event revealed itself as an unusually well-documented example of such a shift. Satellite networks adjusted orbital parameters to account for slight variations in Earth's gravitational field. Positioning systems refined calculations to maintain accuracy at the centimeter scale. The synchronization of these systems allowed for a comprehensive reconstruction of how the planet responded in real time to a sudden redistribution of mass. Beyond the immediate geophysical effects, secondary geological responses began to draw attention. Volcanic systems within the region exhibited signs of heightened activity following the earthquake. In particular, eruptions were observed at volcanoes that had remained dormant for extended periods, releasing ash plumes rising several kilometers into the atmosphere. One plume reached heights of approximately 7 kilometers, or about 4.3 miles, while another extended to roughly 6 kilometers, or 3.7 miles. These eruptions highlighted the interconnected nature of tectonic and volcanic processes, where stress changes induced by seismic events can alter the state of nearby magmatic systems. The relationship between earthquakes and volcanic activity remains complex. Not all large earthquakes trigger eruptions, and not all eruptions follow seismic events. However, the Kamchatka sequence provided a clear example of how stress redistribution within Earth's crust can influence multiple geological systems simultaneously. The release of pressure along one section of a plate boundary can transfer stress to adjacent regions, potentially destabilizing magma chambers or altering pathways for gas and molten rock. As the flow of measurements continued from satellites, ocean buoys, seismic arrays, and deep Earth sensors, the full scope of the planetary adjustment began to sharpen with increasing clarity. The Kamchatka rupture did not end when the shaking stopped. It initiated a cascade of recalibrations that moved through Earth's systems in ways both immediate and delayed. Each dataset added another layer of resolution, revealing how a brief release of tectonic strain could propagate into long-term geophysical consequences. One of the most striking developments came from global positioning networks, which detected persistent ground deformation well beyond the immediate rupture zone. Stations distributed across northeastern Asia registered subtle but measurable shifts, in some cases on the order of several centimeters, or roughly an inch or more, even at distances of hundreds of kilometers from the epicenter. These displacements were not random. They followed coherent patterns consistent with elastic rebound, the process by which the crust adjusts after a sudden release of accumulated stress. The land, once compressed and distorted by years of tectonic loading, began to relax into a new equilibrium. In the days that followed, interferometric synthetic aperture radar operating from orbiting satellites produced highly detailed deformation maps. These maps revealed not only the primary rupture, but also secondary faulting distributed across a wide region. Some areas experienced uplift, rising by several tens of centimeters, while others subsided by similar amounts. In coastal zones, even modest vertical changes had important implications. A rise of just half a meter, or about 1.6 feet, can alter tidal patterns, expose previously submerged features, or disrupt marine ecosystems adapted to specific water depths. Oceanographic instruments added another dimension to the unfolding picture. Pressure sensors, anchored to the sea floor, recorded the passage of tsunami waves with remarkable precision, capturing their speed, amplitude, and frequency as they traversed the Pacific. These observations fed directly into refined models of wave propagation, improving the ability to forecast arrival times and intensities for future events. The Kamchatka tsunami, while less destructive than feared across most regions, provided a valuable real-world data set for testing and enhancing predictive systems that protect millions of people living along vulnerable coastlines. At the same time, gravitational measurements began to reflect the redistribution of mass caused by the earthquake. Satellite missions designed to map Earth's gravity field detected minute variations, indicating where mass had been concentrated or depleted. These shifts, though extremely small in absolute terms, are critical for maintaining the accuracy of navigation systems. Even a deviation of a few microgals can influence orbital calculations, requiring adjustments to ensure that satellites remain precisely aligned with their intended trajectories. Atomic clocks, operating with extraordinary stability, continued to register the subtle acceleration in Earth's rotation. The shortening of the day by a few microseconds may appear insignificant, yet it carries profound implications for timekeeping. Coordinated universal time, which underpins global communication, navigation, and financial systems, must account for even the smallest irregularities in Earth's spin. While the change induced by the Kamchatka event did not necessitate an immediate adjustment, such as a leap second, it contributed to the cumulative variability that timekeeping authorities monitor continuously. The redistribution of mass also influenced Earth's oblateness, the slight flattening at the poles and bulging at the equator that arises from rotational forces. Changes in oblateness affect how mass is distributed relative to the rotational axis, which in turn feeds back into the planet's moment of inertia. Although the variations caused by a single earthquake are minute, they become significant when integrated into long-term models of Earth's rotational behavior. The Kamchatka event provided another data point in understanding how sudden tectonic processes interact with ongoing geophysical cycles. Volcanic activity in the region continued to evolve as well. The eruptions that followed the earthquake were not isolated bursts, but part of a broader pattern of heightened activity. Ash plumes, rising to heights of 6 to 7 kilometers, or approximately 3.7 to 4.3 miles, injected fine particles into the upper atmosphere. These particles can influence local climate by reflecting sunlight and altering cloud formation. While the scale of these eruptions was not sufficient to produce global climatic effects, they demonstrated how interconnected Earth's systems are, with tectonic forces influencing atmospheric processes. Geochemical monitoring detected changes in gas emissions from several volcanic sites, including increases in sulfur dioxide output. Such changes often indicate shifts in magma dynamics beneath the surface. The earthquake likely altered pressure conditions within the crust, allowing gases to escape more readily and, in some cases, facilitating the upward movement of magma. These processes remain under close observation, as they can evolve over weeks or months following a major seismic event. Beneath the surface, seismic tomography began to reveal how the rupture affected deeper structures within the subduction zone. Variations in seismic wave velocity suggested changes in temperature and material properties along the plate interface. These changes may influence how stress accumulates in the future, potentially affecting the timing and location of subsequent large earthquakes. The Kamchatka event thus contributes not only to immediate observations, but also to long-term assessments of seismic hazard in one of the most active tectonic regions on Earth. Hydrological systems were not immune to the changes. In certain areas, groundwater levels showed measurable fluctuations, rising or falling in response to changes in subsurface pressure. Wells located hundreds of kilometers from the epicenter recorded anomalies within days of the quake. These signals underscore the sensitivity of water systems to tectonic forces, as fractures open or close and permeability shifts in response to stress redistribution. Marine ecosystems near the rupture zone also experienced abrupt changes. The displacement of the seafloor disturbed sediment layers, releasing nutrients into the water column. In some areas, this led to short-term increases in biological productivity as plankton populations responded to the sudden availability of resources. However, the same disturbances also risked damaging benthic habitats, particularly in regions where strong currents and sediment movement disrupted established ecological structures. As data continued to accumulate, computational models were refined to integrate these diverse observations into a coherent framework. High-performance simulations reconstructed the sequence of events from the initial rupture through the propagation of seismic waves, the displacement of the ocean, and the subsequent adjustments within Earth's interior. These models serve as essential tools for understanding not only what occurred, but how similar events may unfold in the future. One particularly important aspect of these models involves the coupling between solid Earth processes and fluid systems. The Kamchatka earthquake highlighted how quickly energy can transfer between rock and water, generating tsunamis that travel across entire ocean basins. By improving the representation of this coupling, scientists can enhance early warning systems, providing more accurate and timely information to populations at risk. The event also underscored the role of dense global monitoring networks. Never before has a seismic event of this magnitude been observed with such extensive instrumentation. From satellites orbiting thousands of kilometers above the Earth to sensors embedded deep within the crust, the array of instruments captured the event in unprecedented detail. This level of observation transforms a natural disaster into a source of knowledge, enabling a deeper understanding of the planet's dynamic behavior. At a broader scale, the Kamchatka rupture fits into a pattern of mass redistribution that includes both natural and human-driven processes. While earthquakes produce sudden shifts, other factors such as glacial melting, sea level rise, and large-scale groundwater extraction contribute to more gradual changes. These processes collectively influence Earth's rotation, its figure axis, and the distribution of mass across its surface. The comparison highlights an important point. The forces shaping the planet operate across a wide range of timescales, from seconds to decades. Despite the measurable changes recorded after the earthquake, the overall stability of Earth's system remains intact. The planet continues to rotate with remarkable consistency, its axis maintaining the orientation that governs seasonal cycles. The adjustments observed are part of a natural equilibrium, a continuous balancing act driven by the interplay of internal and external forces. Yet the significance of the Kamchatka event lies in its ability to reveal these processes with unusual clarity. It offered a rare glimpse into the mechanics of a living planet, where even the smallest measurable changes can be traced back to immense forces operating deep beneath the surface. The event demonstrated that Earth is not a static sphere, but a dynamic system, constantly adjusting, redistributing, and responding to the forces that shape it. And if this deep dive into the hidden forces shaping our planet sharpened your understanding or gave you a new perspective on how interconnected everything truly is, go ahead and like, share, and subscribe. Do not forget to tap that hype icon to help this reach a wider audience.